who is associate professor at the Faculty of Math and Physics here at the University of Ljubljana. He is also a member of the Quantum Materials Group in Joseph Stephen Institute, and he is also the head of the laboratory for measurement of large-scale user facilities. And so now he will present his thought about experimental signatures of quantum physics.
Thank you very much for this introduction. Can you hear me well? It's not too big of a yeah, I would like to start with thanking the organizers, of course, for inviting me to present our work or kind of things that we do here at the Joseph Institute and also the University of Ljubljana. So I'm affiliated with both institutions. So today I'll talk about the experimental signatures. And you'll see an experimentalist point of view of quantum liquids. You've had already quite a nice introduction to these topics, right? As I understand. So I'll really focus on the experimental part and only give you a brief introduction into some of the properties of spin liquids, just to start with. So let me introduce again the facilities where I work. So I'm employed at the Joseph Stephen Institute, which is just across the street, as you already know by now, I guess. And I'm a part of the quantum materials group there. So these are the members. This was a gathering at the conference last year, to which we all went. This was in Dresden. It was a really nice conference on NMR pillar. So I'll explain some of the techniques that we use for our investigations. And first of all, these are some more traditional techniques, namely the electron spin resonance and the NMR, so nuclear magnetic resonance. Both techniques we use here locally at the Joseph Stephen Institute to investigate quantum materials or quantum spin liquids also, of course. But lately we've added some new techniques to this, and this includes measurements at large-scale user facilities, which is MUSR, so muon spectroscopy or muon spectralization. I will also introduce this technique later on. Neutron scattering, I will probably talk about neutron scattering at the end, if there is enough time left for that. And this includes also other techniques like measurements in high magnetic fields, with, of course, traditional techniques like electron spin resonance. In high fields, sometimes high fields are required to give you a better resolution and stuff like that. And these measurements we also do quite regularly in the National High Magnetic Fields Laboratory in Florida. Okay, so I'm the head of this so-called laboratory for measurements at large-scale user facility, where we mostly focus on these techniques, but also on the traditional ones, ESR and AIM. Okay, so the field of research will be quantum spin liquids. So let me give you a really short introduction into quantum spin liquids. So quantum spin liquids are, of course, interesting state of matter. Why they are interesting? Because they are different to ordinary paramagnets on one hand, and also different from the order state, from the magnetically ordered state, right? So these states are characterized by the lack of long-range magnetic order. But still there are correlations, or there is a strong entanglement, quantum entanglement present in these states. And this is something that we want to focus on. Okay, what is the motivation for studying the field of quantum spin liquids? The motivation is twofold. From one perspective, it's the fundamental science, right? So these are, as I said, novel quantum states of matter. And some novel phenomena can be found here. I will give you some results or present you some results of our findings in this kind of systems. So this is just a sketch of what was found in one of the materials. Namely, I will present two phenomena which are actually common to metals, yeah? So to conducting systems, but we found the analogs, magnetic analogs in the insulating systems, right? In quantum spin liquids. And this will be pairing of spin-ons, which are the excitations in the systems, which is analog of superconductivity. And I'll also give you some results about spin-on Kondo effect. Again, Kondo effect is something known from the matter. And I will explain later a bit more about it. Okay,
These states have some unusual properties, and because of that, the states are also, of course, interesting from the application point of view. I'm sure you heard about that during this school here about topologically protected quantum computing, so I won't go into any detail. Okay, so a quick introduction into quantum spin liquids. So what I'm showing here is a pair of spins. As you all know, if the spins are interacting, yes. So if the spins are interacting antiferromagnetically, you can form a classical state, meaning one spin pointing up, the other down, or vice versa, right? And this will give you the energy given here. Okay, if the spin is, of course, one constant spin. Okay, but then if you make a quantum superposition of the two states, up, down, up states, yeah, you gain energy, or you get a state which has much lower energy than the classical state. And this is a quantum mechanical state. Okay, and this phenomenon actually is something that was known already in chemistry, for instance, and it was introduced to chemistry by Linus Pauling in 1933, where he was studying, or he was proposing, what is the structure of benzene. So benzene was, of course, a well-known molecule, but the exact structure was not known at the time, and all the positions of the structure for this molecule, none could explain its chemical properties. So it was Pauling who proposed that there is actually a resonance between the states. Yeah? So the resonance in the sense of these double bonds between C atoms. You see? And if there is a resonance, in chemistry we basically this circle, yeah, in the C6 ring tells you that these electrons or double bonds are not localized, but are actually the property of all the carbon atoms. Now, in a similar manner, in magnetism, this kind of resonance was first investigated by Philip Anderson. This was in '73, and he was investigating the ground state of Heisenberg lattice, Heisenberg triangular lattice, so two-dimensional model, very simple one, isotropic, and he was investigating what would be an alternative to a classically ordered Néel state. Okay? And he proposed that one could point these these valence bonds, which are simply singlets. So singlets are no valence bonds. You can put them on a lattice, rearrange them in many different arrangements, of course, and then if you make a linear superposition of all the possible states, you get a candidate for the ground state. Right? In this state, he also estimated what would be the ground state of this kind of arrangement, or this kind of state, and he found out that it's really actually quite close to what you get classically for the Néel state. So he proposed that to be the ground state. Later on, it turned out that this is not the real ground state of the triangular lattice in the case of the Heisenberg spins, and actually the state that occurs is this classical one, which is the 120-degree arrangement of spins on the triangles. But nevertheless, this is very important because this is regarded as basically the introduction of the concept of quantum spin liquids. So from here on, the quantum spin liquid phenomenon or field went on. Okay, so where to look for quantum spin liquids? One thing that you usually need is so-called magnetic frustration. So what magnetic frustration means, you probably already know. Let's imagine that you have a triangle of spins, which are now Ising coupled, so that the picture is easier to understand. So your states, you have 8 states, right? 2 to the power of 3 different states. And out of these 8 states, 6 states have configurations like this. So 2 spins pointing in the same direction, and the third one pointing in the other, different direction. And all these spins have the same energy, of course. Yeah? And they give you the ground state manifold of this very simple system. So whatever you do with your spins, you will never get all the bonds to be satisfied at the same time. So at most, you will have 2 green bonds, so these are the satisfied bonds, and 1 bond will remain red, unsatisfied. Okay? And this is simply due to the geometry of the system. This triangular motif prevents you from classical Néel ordering, where all the bonds would be satisfied at the same time. You can have frustration also resulting from exchange, competition of exchange interactions. Let's say that you have now a square lattice. So square lattice is not frustrated if there are only interactions between nearest neighbors, right? But then if you introduce additional interactions between on the diagonals, yeah, you get frustrated. You get this triangular motif, and there is a frustrated region. Yeah, and then depending, of course, on the size of the nearest neighbor interaction in comparison to the next nearest interaction, the system is more or less frustrated. Okay, good. So what are basic ingredients of quantum spin liquids? One of the main ingredients are so-called quantum fluctuations. So quantum fluctuations are fluctuations which prevent your system from ordering, even at zero temperature. And these quantum fluctuations basically come alive already from the Heisenberg uncertainty principle, yeah, because you can never really determine the value of all the components of the spin at the same time, you know, right? And the quantum fluctuations are particularly strong if you go to lower dimensions. So if you reduce your system from 3 to 2 dimension, or even more to 1 dimension, they become even stronger. And they are also very strong, or becoming stronger, when you reduce the size of the spins. Yeah? So simply comparing the classical energy to the quantum energy, this comparison is getting, the difference between the two is getting bigger and bigger as you reduce the size of the spins. So one very important property is also quantum entanglement. So the singlet states are maximally entangled. But now what you want to have on an extended lattice is actually macroscopic entanglement. Okay, so that you have entanglement on like a macroscopic property of the system, this entanglement has to be essential for the properties of the ground state. So the excitations, for instance, are predominantly given by this entanglement, and these excitations now are different from classical spin waves, which you found in magnetically ordered state, and one possibility is shown here. So let me wait until this picture comes back, this movie comes back to the beginning. So you can imagine that if you have this state, you can induce an excited state on one of the bonds by simply flipping the spins both pointing up, right? And then if you rearrange the position of the valence bonds, this means that these excitations, which are now so-called fractional excitations between, because each excitation carries spin 1/2 degree of freedom. Yeah? So when you make a spin flop, this is a spin 1 excitation. But this is then decoupled into 2 excitations. Yeah? 2 spins that, or 2 spinels to be exact, which can travel around by simply reorienting the valence bonds, right, on the lattice. So these are fractional excitations which can behave as quasi-particles. What is also very important or very interesting about these excitations is that because they are created in pairs, okay, this is now another example on a one-dimensional chain. Again, you can make an excitation by flipping one of the spins, right? So this is spin 1 excitation. Yeah? But then you can rearrange these spins in between, so this domain balls now, which are the excitations, can move, freely move left or right. Okay, and now you end up with, of course, 2 such domain balls, 2 spin 1/2 excitations, which are therefore fractional excitations. Now, the energy that was given to the system by flipping the spin is now divided into two excitations. Because of that, the spectrum of such excitations is continuous. Yeah? So you have a continuum of excitation. Let's say if you choose a given wave vector, you would have magnetic excitation, which can have a range of energies, and they can divide, of course, between themselves the energy that was invested in the system. Okay, and then the last property, and I will finish with that, are gauge fields, emerging gauge fields, which are again a property which emerges in the picture of low energy picture, if you want. These gauge fields also have their own excitations. They have some special symmetry. I will not go into that. But what is also important is that they can through these gauge fields, the interaction between those quasi-particles, the spin of quasi-particles, are also mediated. So they are very important from this perspective. Okay, so that was the introduction that I was telling you about. So it was very short and not really involved, right? So I hope you understood everything. So now I will continue with the experimental part, and I hope it will be light enough for this late hour in the afternoon. But if there is some question in between, because it's a long lecture, if there is some question in between, don't be afraid just to ask. Raise your hand and you can ask whatever you want. Right? You don't have to wait until the end of the lecture. Okay, so let me move to the experimental part now. This is a paper that we had recently, a review paper. If any of you is interested in the experimental part of experimental insight into quantum or topological states, you're welcome to read this paper. I will just give you some examples which were presented in this paper. And namely, I will focus on a few techniques, mostly on the local probe techniques, so the electron spin resonance. This is our lab at the Joseph Institute. Nuclear magnetic resonance, again, our lab at the Joseph Institute. And then I will focus on muon spectroscopy, which is here. So this is a lab at PSI, at Power Sharing Institute in Switzerland, where we do regular experiments. And at the end, I will also briefly talk about neutron scattering experiment. Again, this is an example of a neutron spectrometer. Actually, it's the diffractometer, time-of-flight diffractometer at the Rutherford Appleton Laboratory in the United Kingdom. Okay, so let's start with ESR. I will shortly introduce the techniques and then show some results. So what can you learn about quantum spin liquids from this kind of experiments? I guess you are familiar with this technique more or less, right? You've heard about electron spin resonance. It's very similar to NMR, to nuclear magnetic resonance. So it's the same principle in principle, yeah. So what you do is you put your system in a magnet, and the magnet splits the states. If the states are simple spin 1/2 states, then you would end up with 2 levels, right? And then what you do is you try to excite the system, or you try to irradiate it with some microwave source, where the magnetic field is perpendicular to the external magnetic field, and this induces transitions. Yeah? The transition will be induced if the frequency of your additional source, of the microwave, is, or the energy, if you want, is in line with the Zeeman splitting. Okay, in this case, you will get here, yeah, you increase the field, yeah, and then you get a peak, an absorption peak. Okay, so this is the main, the basics of it. So typically, this is then an absorption spectrum. What you measure is an absorption spectrum. Actually, you measure by a derivative of it, but it's not important at this point. What is more important is what kind of information can you get from this kind of spectrum, right? So the ESR spectrum actually is proportional to the second derivative to the imaginary part of susceptibility, spin susceptibility, which gives you actually temporal correlations of magnetization, which is perpendicular to the static magnetic field. Okay, this is what you measure. So you measure basically a Fourier transform of this kind of correlations. And these correlations are determined then by the Hamiltonian of the system, which determines what is the time evolution of the magnetization, right? Okay. Good. So then, what kind of information can you extract from this? One thing is the intensity of the line. So the ESR intensity directly gives you local static susceptibility. Yeah? So this is proportional to static susceptibility, and this is measurement on local scale. Yeah? Compared to Bath measurements, which you usually do, let's say, by squid magnetometer. I will compare the two later, as you will see. Then the second information is the position of the resonant field. The position of the resonant field, if you are in a crystal, it's given basically by the interaction of the spins, which are localized somewhere in your crystal, to the neighborhood. Yeah, so the electrostatic neighborhood actually affects already the position of the line. Plus, the position can also depend on magnetic anisotropy, as I will show you in one of the examples later on. Then the third parameter of the ESR is the line width. Now the line width is directly can give you a direct measurement of the magnetic anisotropy. This is because the magnetic anisotropy is the term which actually gives a finite line width to the ESR line. If the interaction is isotropic, like only Heisenberg interaction, then you would end up actually, in ideal case, of course, with a delta function as a response. Okay? So your anisotropy is a direct measurement of the anisotropy, magnetic anisotropy that's present. Okay, it can be also due to some lifetime broadening effects, like if there are phonons present in the system, they can give you some broadening of the resonance lines and so on, but these are more details, not important for the demonstration of the technique. Okay, the advantages of the techniques are the following. So with ESR, you're directly measuring the speed, right? So this is an intrinsic probe of intrinsic and direct probe of electronic spins. So you're directly measuring the spins which are doing something to your system because of the interactions between them, right? This is different to NMR, for instance. In NMR, it's going to again be an intrinsic probe, but not a direct probe, because we'll have another probe and some nucleus in the system which will be interacting with electrons. But here we are measuring directly the electrons. The second advantage of ESR is that actually it usually requires quite small, let's say, small number of spins in relative terms, of course, meaning that typical samples that you would measure would be of a few milligrams, maybe, up to 100 milligrams. It's usually more than enough. It depends a little bit on the width of the line. The broader the line gets, of course, the bigger, the smaller signal-to-noise ratio gets. So in principle, if you have really broad lines, then of course you need more sample. But in principle, for narrower lines at least, it's only a few milligrams that you need. Then the last advantage, or one of the advantages also, is that you have quite a good resolution of the order of 10 to minus 4 to 10 to minus 5. So you're really precise in determining the position of your line. Okay, so now let's go to examples. So first example that I will show you is an example on Herbert split type, which is one of the best studied examples of the Kagome lattice. So Kagome lattice, probably you've heard about this during this school, right? So it's a lattice which is based on these triangular motifs. So these triangles are now occupied by copper 2+ spins, which are spin 1/2 entities. Okay? And these triangles are corner sharing, as opposed to the triangular lattice, where the triangles of spins would be edge sharing. So here, each spin only has 4 nearest neighbors. Okay? For this particular compound, it is well known that there is structure disorder present in the system. Meaning that some copper ions tend to go on the zinc side. So this black point here is the zinc side, which is, again, zinc 2+, non-magnetic. So in principle, by the way, this is interlayer side. So this would be layers. So this is a picture of the layer, but then the layers, so this is then the C direction, right? So these are the layers, and in between the layers, you have the zinc sides, which are in principle non-magnetic. But the problem is, as I said, that there is structure disorder. So some of the copper sides tend to go on the zinc side. Okay? So you would never get a perfect structure, which is simply, well, given by the chemistry. Yeah? You never end up with a perfect structure. So you always have this structure disorder present in the system, which is important. I will tell you later on. Okay, so this is now the measurement of the ESR spectra, a comparison of two spectra at 300 and at 10K, I guess. I guess you cannot see it. Because you know I cannot see it. Yeah, it's better solution here on this screen. Anyway, so here is the temperature dependence of the intensity of the signal, and one needs to compare this to the temperature dependence of the susceptibility of the. Yes, please.
By structural disorder, do you mean that the nuclei of the
copper? Yeah, copper ions. Copper ions get also on the zinc side, and some zinc sides in principle also occupy the copper. Yeah? So you get some vacancies, in principle you get some vacancies in the Kagome lattice because of the zincs coming to the Kagome layer, and on the other hand you get copper ions which are non-magnetic and they connect the layers. Yeah?
So then I have 2 ions.
Sorry?
I have done 2 ions almost.
No. They just exchange.
Where's the
Vacancies in terms of magnetism. If there is zinc, there's what vacancy? Magnetic vacancy. It's not like a structural vacancy. Yeah. Okay. So the temperature dependence of the intensity, SR intensity, has to be compared to bulk measurements, and this is this here, this curve here. And bulk measurement, on the other hand, you can measure the susceptibility of the intrinsic cogonocytes by NMR. Yeah? And the result is shown here. So the intrinsic susceptibility of the cogomer layer is very different from the bulk measurement. Why is that? This is exactly due to the structural disorder. So the coppers that come to the zinc site, they are very poorly coupled between themselves or with the cogonocytes, and as a result, they behave as quasi-free spins. And this gives you, well, the Curie-like dependence on the susceptibility. Yeah, so if you go to really low temperatures, the susceptibility, the bulk susceptibility, is dominated by this so-called defects. Let's call them defects. Okay? While the intrinsic spins, the susceptibility of the intrinsic spin gets really long. Really low. And this means, of course, that it's very hard to determine it unless you have a probe how to measure it separately, right? And this can be done by NMR. I will show another example later on, some NMR results, but not this one. Okay. So what can one deduce from this is that, of course, as our intensity follows the intensity of the bulk magnetization, obviously we are measuring both the defect spins and the intrinsic spins. And since we only see one line, it means that there has to be significant coupling between the two types of spins. Otherwise, you would get two separate lines. Okay? So this is the first conclusion that one can make. Okay, so now these are the measurements of crystals that were powders. These are crystals now. So you can measure this line as a function also of the orientation. So H parallel to C would mean a magnetic field perpendicular to the cogomer layers, and this is in the cogomer planes. Right? And what you can see is that you have, of course, this dominant broad line in both cases. And this gives you the temperature dependence of the susceptibility. You can fit it with Curie-Weiss law, and you can see that there is an effective coupling between these defect spins, which is of the order of a few Kelvin. Okay? And because of this coupling, this also explains this coupling is bigger than the splitting of the two lines that you would expect for copper spins in a field where the experiments were done, which was in this case estimated to about 2 Kelvin. Okay? And because this coupling is bigger, you get this exchange narrowing of the two lines, and you end up with only one line. Even though there are two types of species that contribute, or two types of centers that contribute to the signal. Right? Okay, so this is this broad line. But then it turns out that there are also some additional lines you can see here probably. Right? So in the case of in-plane magnetic field, there are 3 additional very narrow lines, while in the case of the field perpendicular to the cogomer plane, there is only 1 additional narrow line. So if you focus on the 5K spectrum, you would see here is a broad line, and then there is this narrow line here. Okay? And in this case, obviously, so there is a second defect site present in the system, and since we see 3 different lines, at least for the case when the magnetic field is in the plane, this means that the coupling of these defects to the surrounding defects or whatever has to be small, has to be much smaller than the energy of the energy difference in the magnetic field due to Zenon splitting. Okay, and what is interesting is, of course, this second defect acts like being now almost free. So if you fit it with Curie-Weiss law, you would get Curie-Weiss temperature which is 0. Yeah? But actually, it turns out that a better fit is obtained if you assume that there is some power law dependence of the susceptibility, which is, of course, a bit strange. Huh? Okay, so we have 2 types of defects. Now, additional insight that you can get is from angular dependence of these 3 narrow lines. So what I'm plotting here, these are the narrow lines, and this is the broad line. So the broad line is the one that does not change the position much when you change the field within the cogomer plane. While the narrow lines give you this oscillation, 180-degree oscillation, what you would expect. What is interesting in this case is that you don't have the threefold symmetry that you would expect to have for the ideal structure. Yeah, so for the ideal structure, also this data set here should have the same height as the other two data sets. And since it does not have, this means that the symmetry is locally broken. Okay? And you can estimate what is basically what is the difference of the ING factors, which is really small, and it's really hard to observe by any other technique. Actually, we have another technique we also measure to observe the symmetry breaking by magnetic torque measurements, which were combined to give these estimates of the G factor anisotropy within the plane. So what is important is that this measurement was the first measurement that showed that there is structural distortion of the Kagome lattice, which was of the Kagome lattice in the case of Herbert-Smith, which was not known before. Okay, and this structural distortion, of course, can affect a lot of the ground state. Huh? Okay, so let's move on. ESR line width. So I move now to ESR line width. Now ESR line width, as I told you before, is given by magnetic anisotropy. Or magnetic anisotropy is the one that determines the ESR line width. And the dominant magnetic anisotropy in this case is the so-called Jelshinsky-Maria interaction, which again I'm sure you know about, right? So it has this form here, and for the case of the Kagome lattice in Herbert-Smith type, it has this pattern of speed. So it has two components. One component which is not clearly seen as see here. So there is a component perpendicular to the planes, and there is then, so this is this circle with the dot in the middle, which can be hardly seen. But then there is also another component which is the in-plane component. And by its direction is determined by the symmetry of the crystal. Okay? Yes. Okay, so how the magnetic anisotropy comes into the ESR line width? One can use the so-called Kubo-Tomita approach, which is an approach which is valid in paramagnetic case, so you have to be at high temperatures, but ideally at very high temperatures compared to J, of course, so the line width is not temperature dependent. And then in this limit, you can estimate the so-called moments of the resonant line. The moments are given here. So this is the second, this is the fourth moment. They are given by these commutators of spin operators with H prime. H prime is the anisotropy Hamiltonian. Okay? Only the anisotropy is Hamiltonian is something that gives you finite M2. This is something that I want to stress again. Okay? The isotropic part gives you 0 M2. So it doesn't give you any line. Okay? Okay, so now in this case, one can then calculate what would be the line width as a function of orientation. And so here are the measurements of the two principal orientations. This is perpendicular and in-plane component. And by the anisotropy, from the anisotropy of the line width, one can then estimate, by calculating these moments and evaluating the line width, one can estimate what is the chi-square of a fit for a given set of parameters. Okay, so here I'm plotting the out-of-plane component versus the in-plane component, and I'm plotting the chi-square of the fit. Okay, and the best agreement is observed here. Yeah, so we can quite well determine what is the out-of-plane component of the Jelshinsky-Maria interaction. It's 15 Kelvin. You have to compare this to 180 degree approximately, which is the isotropic coupling. Yeah. While on the other hand, the component which is in plane is less well determined, but it's definitely small compared to the out of plane. Yeah. So the dominant Jelshinsky-Maria interactions are these circles really, or the dominant component are these circles which are all pointing in the same direction. Okay. Why is this important? It's important because it was theoretically predicted that the Jelshinsky-Maria interaction can affect the ground state. If it is 0 for the Kagome lattice, there is a consensus that there is a quantum spin liquid ground state. Okay? It's not known yet what kind of quantum spin liquid there is, but definitely there is a consensus that there is a quantum spin liquid state. But then, if you introduce the Jelshinsky-Maria interaction, this perpendicular component, yeah, if you increase it, at some point you're stuck with this quantum critical point. So at this point, what happens is that if you go beyond this point, you enter into a Nel state, into a magnetically ordered state. So what is plotted here is actually the size of the moment as a function of Jelshinsky-Maria interaction. Yeah? So for your Jelshinsky-Maria interaction, it's just small, yeah, you would get 0 moment, but then at some point there's a quantum critical critical point, and you would enter an else. And it turns out this Herbert-Smith type actually is located quite close to this quantum critical point. So quantum fluctuations could be important. Yeah? So it's an important experimental insight to the theoreticians to also consider the effect of geosystem interaction, because it's obviously quite close to the quantum critical point.
Wait,
Yes?
sorry, is this numerics or experiment?
That's experiment.
How do you
you mean this?
Yeah, this one.
No, that's numerical. Yes. That's theoretical. Yeah.
Thanks, God.
That's theoretical. Prediction. Okay. Okay, then there is another system which is also kind of interesting. Its structure very similar, so it's also based on another Kagome lattice based on copper spins. Yeah. And now instead of zinc, we have yttrium, and yttrium ions are much more different from copper than zinc ions are from copper. And because of that, you don't have any structural mixing, as in the case of Herbert-Smith type. So from this point of view, it's much cleaner, this compound. Yeah. Okay. So again, we did the same, more or less, the same job as with Herbert-Smith type to determine the Jaushinski-Maria interaction. In this case, actually, it turned out that we were not able to, from ESR, we were not able to measure the anisotropy of the line, which is a necessary input to include in your in this expression on the previous slide, yeah, which give you then independently both of the components of the Jaushinski interaction. In this case, it was not possible because the line was simply too broad, yeah, so you cannot distinguish between the two orientations experimentally. So we had to also introduce other techniques. So ESR simply gave us this upper bound here, this one here. So for a given in-plane component, you can get the out-of-plane component, but you cannot determine their size separately. But on the other hand, you can use some other techniques. It turns out that magnetic heat capacity, yeah, the magnetic heat capacity is very much depends on the size of the out-of-plane component. And from the heat capacity, we did some calculations of how this heat capacity changes with the size of the Jaushinski-Maria interaction, and we were then able to determine this curve here. And then also from the magnetic susceptibility, from bulk susceptibility, we can also make an estimate of how this would change with the size of both components. So the ideal range of, yes?
I have a question.
Yes.
In order to relate these parameters with heat capacity, one would need some theory of this in liquid state.
It was, so these are finite size Lanczos method, finite temperature calculations. Yeah? So that's the theoretical part. Yes.
How, I mean, the specific heat and flow energies is not something you easily get out of Lanczos. And the higher energy.
Well, definitely you get something which is magnetic, right? And there are two contributions actually, specifically. So I'm only showing this low temperature part. There is a peak or a maximum which is attributed to correlations within plane. Yeah? And this is something well known from the studies, from different studies.
The Schottky anomaly you can get from any number of mechanisms.
Yeah, sure. But what I'm saying is that at low temperatures you get this additional peak, which then determines, which depends on the anisotropy itself. Yeah. Yeah.
It's literally anything.
No, but it's not a Schottky-like anomaly because it doesn't change its field. So it's really, I mean, it's not this ordinary Schottky-like where you would just simply split the two levels by field.
No, but if you've got such a big discrepancy in energy scales,
Yeah.
I'm just not sure that with Lanczos you can actually resolve polytonic problems.
Well, I'm not an expert of Lanczos anyway, but you probably know Peter Perosh. It was the one who was involved in probably from our institute, so he was the one performing the measurements and the calculations. And he's so he has quite a long on this kind of systems, right? He has many contributions to the field of quantum frustrated lattices, like triangular or Kagome lattice. Okay, so anyhow, again, we were able to determine the size of the Jaushinski-Maria interaction, and now it turns out that this actually puts you in the field diagram here. So it's well in the ordered part of the field. And actually there is a magnetic transition which occurs below this maximum. It occurs here, but you cannot really see it pronounced in heat capacity. You can see it actually very nicely in neutron scattering. I will show you these results later on. Okay, so this actually does order magnetically. Okay, and then the last insight would be, okay, can you measure with ESR the spin-on excitations, which are like a trademark, right, of the quantum spin states? And there have been some theoretical predictions of that, or so what theory would predict for quantum liquid states, for different kinds of quantum liquid states. But also there has been some an experimental paper quite lately. So this is a couple of years ago. And I will just briefly introduce experimental results here. So in this case, we have a one-dimensional spin chain of copper spins again. Again, we have Dzerzhinsky-Maria interaction. And in this case, remember, the main balls are now the spin-on excitations. Okay? Good. So this is how the experimental spectra look like. So there are two modes, plus there is a small paramagnetic mode, which is simply an impurity mode. It's not important. So essentially there are two modes. These modes shift with field, of course, but they shift differently as a result. They don't shift uniformly with respect to the paramagnetic line. And the two modes you get because of the Dzerzhinsky-Maria interaction, which splits a single mode into two modes then. But if you are in a model of a spin-on gas, which is given by this Hamiltonian here, so these operators here would be operators for right-moving and left-moving spin-ons, and their interaction with the magnetic field. But this is still a spin-on gas, so there is no interaction between the spin-ons in this model for now. And in this case, you would get a symmetric splitting of your line. So your position would be displaced from the resonance line by plus minus the size of the Dzerzhinsky-Maria interaction. Okay? On the other hand, if you allow backscattering, the interaction between spin-ons, then you open a gap here, so the gap at zero momentum. And what is even more important is that the energy dependence, the field dependence of the energy, or the frequency if you want, is not symmetric anymore, with respect to the resonance line. So how does it compare to the experiment? So here is the frequency versus field, or a relative frequency, or frequency shift in comparison to the resonance line versus field, right? And for the spin-on gas model, you have this symmetric splitting, as I said before, which are these two curves here, the dashed lines. And this is obviously not in line with the experiment. What is in line with the experiment is that one of the modes shifts much more than the other mode. And this is what you can see here. And from this, what the authors were able to determine from this experiment was actually first the size of the Dzerzhinsky-Maria interaction, which, as I said, gives you this splitting here. Plus, they were able to basically determine this backscattering term. What is the size of this term? Okay, this is here. Sorry, here. So backscattering now causes this asymmetry in the two terms, and from the experiments they were able to determine the size of this backscattering mode. Okay, so let's go further. So are we on time? No, still have some time, right? Okay, so the next technique that I will focus on is nuclear magnetic resonance. Now, nuclear magnetic resonance, as I already...
Just before,
yes.
What you show right now was about spin-ons in one dimension.
Yes, yes.
Is something like this in 2D?
No, no experiments yet. There are some theories, as I showed you before, but no experiment that I would be aware of. Yes. Okay, so nuclear magnetic resonance, the nuclei are again intrinsic pro because they are present in your sample, right? You can use the nuclei that are in a certain sample present, but now you're not measuring directly, you're measuring indirectly through the coupling with these nuclear modes. Okay? Okay, again some basics about the techniques. So you have nuclear moments now on certain positions in your lattice. Now, if you increase the field, of course, they will polarize the moments. But then if you, so this is now the polarization of the whole sample. But then if you add magnetic field which is oscillating in the direction perpendicular to the external field, you will induce transition between quantum levels, right? Which classically means that your spin will start processing, okay? And changing orientation, of course, because we are changing the Z levels, average Z levels. Okay, and now if you measure a spectrum, of course, the position of the spectrum will be determined by this precession frequency, and this will give you the size of the field. Yeah, so if you measure the position, you measure the local field at the nuclear site. Okay, then you can add some electrons. Let's say that electrons also produce some static fields. This will give you a shift in comparison to this so-called Larmor frequency with no additional magnets, right? And if these electrons fluctuate, so they will produce fluctuations, and these fluctuations would mean that your polarization will eventually return to equilibrium position in external magnetic field, because you induce, again, transitions between Z levels. Okay? So this is the basics of NMR that you can work on from the experimental point of view later. Again, some advantages. One of the advantages is that there is a broad variety of nuclei that you can use. In principle, in any of the compounds, you will find something. Almost in any of the compounds, you would find some nucleus on which you can make experiments. And usually, these nuclei have quite different Larmor frequencies, precession frequencies, which simply depends on the size of their nuclear magnetic moment. And there is a broad variety of nuclear magnetic moments. As a consequence, the frequency in which you can make, the range of the frequencies in which you can make an experiment is quite broad, something like from 10 megahertz to gigahertz approximately. And the spectral resolution here is even better than with ESR. So it's the order of ppm. So you can detect really small shifts. Yeah? And the small shifts can come from the static electronic fields, right? So you can measure these electronic fields in principle quite well. Okay, so what you need here is the coupling, hyperfine coupling between the nuclear spin, the nuclear magnetic moment, and the electronic magnetic moment. So electronic magnetic moment gives you some magnetism which you want to investigate, right? And if there is a coupling, hyperfine coupling of such form, as shown here, you can, of course, locally measure or measure local fields. Okay? This would be local field, or in other sense, you're measuring basically the components of the spin, right, through the hyperfine coupling. Okay. As it was shown on the previous slide, if you have some static electronic field that you add to your external field, this would cause a shift from the resonance so-called Larmor position. This is so-called night shift, which can be measured. So this is simply a shift of the resonance frequency from the frequency in case there was no magnetism. And this is a measure of local susceptibility. Static, uniform local susceptibility. Okay? So this is what you measure by night shift. Okay, again, let's go to an example of that. So here what I'm showing is another Kagome compound. In this case, it is called zinc proctentite. The crystal structure is given here. Again, magnetism is due to copper 2+. And in this case, we also have, like in herbert-smithite, we also have zinc 2+ ions, which are now located within the layers, not between the layers. And again, because of the chemistry, specific chemistry, because of the fact that zinc 2+ and copper 2+ are really similar in terms of chemical properties, you get this zinc-copper disorder, again, so mixing of the two sides. Okay? And this causes, again, defects, which are quasi-free. Now, this compound is different from herbert-smithite in that it also has structural distortion. So these hexagons here are not, as you can see, they are not perfect from the symmetry point of view anymore. Okay? So we have this quite large distortion. And also the the average exchange interaction is smaller by a factor of 3 approximately in comparison to herbert. Okay, so let's see what the experiments give you. Okay, first I'm showing here again the bulk susceptibility measurement, which is the black curve here. Yeah, so these are bulk measurements, and there were some attempts actually to separate the defect contribution, which would be the green line here, and the intrinsic contribution. But as I said before, the bulk measurements simply measure everything, so the total response, and it's quite hard to basically differentiate from this bulk measurements to differentiate between different contributions. You can do that by NMR, again, the same as it was shown for the Herber-Schmidt, or in a similar manner that was shown there. Okay, so what I'm plotting here is the nuclear night shift as a function of bulk susceptibility, or temperature. So this is the temperature scale, and this is the bulk susceptibility. And what you can see is that at high temperature there is a scaling, while at low temperatures, the night shift, which is again, I stress, the local measurement of susceptibility. Yeah? So this is local susceptibility. The local susceptibility reaches a plateau, while bulk susceptibility just continues increasing because of the fact that it's mostly due to defects, these quasi-free defects, right? So what this tells you is that you're actually measuring the contribution of defects to the local fields on the NMR side is quite small. And what you're measuring effectively is actually the contribution of the intrinsic fields to the susceptibility. So this is then the intrinsic susceptibility is determined from the NMR measurements. And why this is important is, again, as I told you before already, there is a consensus about quantum spin liquid ground state for the Kagome lattice, but not exactly what kind of quantum spin liquid is realized. Okay, and for different kinds of spin liquids, you expect different kinds of behavior for the magnetic susceptibility. Okay, for instance, if this is so-called Z2 quantum spin liquid, which is gapped, in this case you would get a gapped behavior, so the susceptibility should have this gapped behavior here. If it's Dirac quantum spin liquid, which is gapless, then you would get something which scales to temperature. And if you have a so-called spin on metal, yeah, which is the case of spinons with Fermi surface, yeah, so it's like electrons in a metal, regular metal, they have a Fermi surface, right? And there is a magnetic analog in quantum spin liquids, which is called a spin-on metal, where you have spinons as quasi-particles, again having Fermi surface. And in this case, what you expect is a constant magnetic susceptibility at low temperatures, and this is exactly what we see here. Yeah? So we anticipate that the state that is realized here is something similar to a spin-on metal. Okay. Then there's the fluctuation part of local fields, of course. So this is not static local fields, which give you the shift. And then you also have fluctuations, of course. And fluctuations you can measure through the spin lattice relaxation time, which now is a measurement of this spin structure factor, which is giving you the temporal correlation given here. Yeah? So this is now the spin structure factor. And your NMR now measures, so the relaxation rate is determined by the density of fluctuations of the Larmor frequency. So the resonant frequency, which is determined by the magnetic field. Now NMR is not a Q resolve technique. This is something that you can, of course, learn from neutrons. What is the Q dependence of the spin structure factor? Here we simply average over all the Q vectors, yeah, because it's a local problem. Okay. So these are now the measurements of T1 relaxation time. So there are two, well, one regime which is quite interesting, and this is this regime here, between roughly 1K or half a Kelvin and 10K, or maybe less, actually 2, 3K maybe. So there's a regime where you have this power law dependence of the spin lattice relaxation time. I should stress that for a metal, what you expect is a linear, so this is the well-known Coringa relation in metals. So T1, yeah, spin lattice relaxation time in metals, would give you a linear dependence. So what we see here is something which is quite close to a linear. It's 0.8 instead of 1. Okay? So this is something, again, which talks in favor of the spin on metal state. But then in addition to that, you have there is an anomaly here, so there is critical temperature, and this critical temperature, you see that the spin lattice relaxation time drops suddenly. And in principle, this is something that you usually observe if there is a magnetic ordering transition. Yeah, this is something that you usually see. So below the magnetic ordering transition, there is a fast decrease of the spin lattice relaxation due to the spin wave excitations that are present in the magnetically ordered state. Okay, so this was, of course, the first candidate to explain this critical temperature. And it turns out that actually this cannot give you the explanation what's happening here. Namely, there is nothing happening to the spectra, to the NMR spectra. So again, one usual fingerprint of magnetic transition is divergence, if you want, of the relaxation time. And the other fingerprint is actually that due to the static fields, also the spectrum changes. Okay? It usually broadens or splits in that crystal. Here we don't see anything like that, and from the line actually we were able to estimate that if there is some magnetic ordered part of the magnetic moment, it's really small. It's below 1% or something like that. Okay? So definitely there is no magnetic ordering going on in the system. So then there is another possibility, and this other possibility is that there is some instability of the quantum spin state of the spinometer. Okay, and so for this reason we measured then some extensive measurements of the spin lattice relaxation time versus magnetic field, and we observed that this critical temperature has a strong field dependence. Okay, that's one observation, and the other observation is that the shape of this temperature dependence below the critical temperature obeys this expression here, so it has two contributions. One contribution, which is evident at low temperature, actually, is the same as above the transition. So it's something that's, as I said, given by the spin on metal state. On the other hand, you have this second contribution. Yeah, the second contribution is now gapped. Yeah? This gapped expression. So what we propose that's happening here is that there is some non-uniform opening of the gap on the Fermi surface. And since nuclear magnetic resonance is basically averaging over the whole Fermi surface, over the whole possible wave vectors, right? We are able to observe basically two contributions. And the relative size of this contribution, of the spin on matter contribution, actually decreases with the magnetic field, right? Shown here. Okay, so what's happening, or what's likely to be happening in this case is that, of course, there is, as I said, opening of the gap in the Fermi surface, which is due to pairing of spins. Yeah? So there is a spin-on-spin interaction, which is mediated by the gauge fields, which I said at the beginning. And this process, what happens here is actually an analog of what's happening in the superconductors. Right? So there are Cooper pairs forming there, which open a gap. And similarly here, there are magnetic quasi-particle spinels, which again can interact and pair to form these pairs, yeah, which are gap. And in fact, the scaling of the gap with the critical temperature is something that's known also from the superconductors. So this BCS light behavior. Okay? Sorry, yes.
So what you also mentioned that in your system there's some structural disorder, and what?
Yes.
Can you infer the lifetime of your spinels because of the
structural disorder? Yeah. Okay. You mean from what I was showing just before, not what I was showing in Herbert Smith, yeah?
Yeah. I mean, if you can somehow, maybe you have some additional data on the influence of structural disorder on your spinels?
Yeah, so at the moment actually we are performing some calculations of the exchange companies, which turns out to be quite distributed actually. So this compound is not an ideal case of the columnitis, because we have, so it's likely or not likely, I would say possible at this point, that you have some chains forming. And then you are really closer to the chain limit than to the conglomerate.
Okay, because my question concerns the fact that to obtain kind of non-trivial pairing with zeros at the Fermi surface, you need very clean system. disorder would quickly destroy it. So before going into a statement about non-trivial pairing, I would examine this very simple.
Yeah, as I said, because of this disorder or structure or deformation, it's not disorder, actually deformation, structure deformation, right? Because of this deformation, the exchange couplings are not ideal in the sense of the carbon lattice.
Okay. But otherwise, but in this model, as opposed to, in this system as opposed to the previous one, you don't have any disorder. Like
no, there's also disorder. Yes, there's also disorder. Yes.
Okay.
There's also a component that, in principle, has to be taken into account.
And you don't know its influence on the lifetime of your spin.
Yes.
Yes, for Spinman's interactive modification,
Yeah.
you do not expect BCS relation at all.
Well, there are
If anything, this is argument against this picture. Not
there are different possible coupling mechanisms. Yeah.
doesn't matter.
There.
Does not matter.
Well, I don't know whether it's.
Because when you have a gauge field,
Yeah.
your Spinman excitations are very non-firm liquid-like.
Yeah. Okay.
As a result of the form a gap, you change a lot the one particle spectrum, and the BCS completely fails.
Yeah. Okay. I wouldn't want to argue with you about that because I don't know the details. What I know is that as I said, there are predictions. Okay. Maybe I can show you.
Well, you know,
Sorry.
dishonest theorists can predict anything.
Yeah. Sure. I know. Yeah. Sure. It's always like that, right? So there are theories, and you try to compare, right, to something what is possible. What is predicted for this kind of spin on metal or spin on Fermi surface state is this that there should be a finite temperature where a gap phase is formed, right?
Qualitatively, yes.
Yeah.
Just against 3.9.
Ah, yeah. Okay. This is what you're talking. Yeah. We don't know what is the coupling really. I mean, what kind of coupling there should be, because also the spin dependence is strange, right? Because the critical temperature increases with field. It's not like SA or something, right? So it's quite unusual. Okay, there was another question, yes?
Yes, is there also a physical kind of picture for what these gauge fields are?
Well, that's kind of complicated, yes. It's related to this question there. I mean, it depends really on the quantum spin liquid, really. What kind of quantum spin liquid we have. I'm not an expert on that. I would go into details about the theory.
So in principle, you can take an electron and break it up into two particles, like
Yeah.
two spin on whatever you like.
Yeah.
And then the theory is going to lead to a gauge field just in order to make the description totally consistent.
Yes.
Whether or not this has got anything to do with
experiment? Yeah, that's
is
another
a completely separate question, and whether or not you're capable of guessing the correct answer at the starting point of your theory is something that theorists don't have a very good track record. That doesn't mean that in this particular case it's not.
Yeah, sure. It's just that
I could name many cases where I think people did guess correctly.
Yeah. It's always, it's a tough problem, definitely. And there's another problem, of course, that, theories are usually idealized in a sense of what kind of Hamiltonian they take into account, right? And in real systems, you always have perturbations which are more or less important. Right? It could be this anisotropy. It's rarely taken into account, actually, but it is in some cases. You have this kind of disorder or whatever in your system, and this can be quite important, especially for frustrated systems, because they are, on the really, there is a strong competition between different states, usually, different possible states, and if you add a small perturbation, even can completely change the system. And these perturbations are always, of course, present in real systems. Okay, so let's move on now. So then the third experiment, how am I doing with time? Yeah, okay, still okay. So the third set of experiments will be now muon spectroscopy experiments. Now what is muon spectroscopy? Again, muon is an elementary particle, which you probably all know. It comes from the standard model, so it's one of the 12 elementary particles of the standard model. And it stable particle, so it decays into a positron. If it's a positive muon, as will be the case for the experiment here, so it decays into a positron. But then on the other hand, it's created from a decay of a pion. So pion is made of quarks, of course, and if you want to make this decay happen, actually it has to go through the weak interaction, right? And the property of weak interaction is that it breaks gravity, yeah? Meaning that these two processes which are shown here, so you have a pion which decays into a muon and a muon neutrino, and then you have a mirror image of that. They are not equally probable, yeah? So actually, experimentally what happens is that you get your muon which is always, whose spin is always anti-parallel to the momentum of the muon, okay? In this rest frame. Okay, this turns out to be very important for the technique to work actually later on. And this is something that was experimentally verified already in '57 by Lederman and Garvin, who performed the measurements of the muon polarization for the first time. And what is interesting about their paper is that at the end of the paper, they also predict that this fact that muons are 100% polarized or perfectly polarized in the experiment in the decay could be used as a very powerful tool for exploring local magnetic fields in materials. Okay, this is very similar actually to NMR. Yeah? So if we would be able to, well, when we implant the muons into a sample, these muons, because they are fermions, right? They have spin. This magnetic moment of the muon then interacts with the local field. The same way as nuclear magnetic moment interacts with the local field of the electrons. Okay? The difference, a big difference here is that muons are 100% polarized because of this parity variation. And the second difference is, of course, that this is an extrinsic probe. So you need to implant the muons in your sample. Yeah? So you need muon beam. Okay. So let's go now to the steps of how this technique works. So first, I should stress that muons are produced from pions already in the atmosphere in the high altitudes. So interaction of cosmic rays with atmosphere first gives you pions, and then the pions decay into the muons. But these muons, okay, most of them decay before they reach the surface of the Earth, which the ones that do reach the surface are high energy muons, because for them this, dilatation of time, the relativistic effect, right, is the biggest. So there's a bigger probability for them to reach the surface. Okay, so these muons have relatively high energies, and because of that, they are not really useful for the experiments, of course, yeah? Because you would need a huge sample really to stop. Okay, so what is done in experiments is actually that you produce muons by hitting protons to a target made of some middle-sized nuclei like carbon or beryllium, and one of the products is again then a pion, which decays into the muon. And then you can use these muons here to implement them into your sample. Okay, so the second step is then muon implantation, and as I said before, for this kind of muons which have relatively low energies, these are so-called surface muons now, because they come from the pions on the surface of the target. So they have relatively small momentum. By the way, the mass of the muon is approximately 105 mega electron volts. This is relatively small momentum, right? And for this kind of muons, you need something like a few, it depends on the density of your sample, but you need a few tenths of a millimeter thick sample to stop it. Okay? The stopping time is quite fast, so it's roughly 100 picoseconds. And another important property is that during the stopping process, this stopping does not involve magnetic degree of freedom of the muon. So the polarization, the spin of the muon does not change during this. So when the muons stop in your sample, they are still perfectly polarized. Okay, then as I said before, these muons decay into positron and to neutrinos, and this happens on the time scale of roughly 2.2 microseconds. Okay, and during that time, of course, because the muon is now located in your sample, it interacts with the internal magnetic field. So if there is a static field, it will process, like the nuclear moment, as I told you before. And what is also important is that also this decay here, yeah, so changing muon to a positron and to neutrinos occurs via weak interaction, which means that, again, it breaks parity, and as a consequence, the positrons that are emitted when the muon decays are preferentially along the direction of the muon spin. Yeah, so if you have a muon, okay, we'll see it on the next slide. Okay, I'll come back to that. First of all, where you can do this kind of experiments, there are 5 facilities worldwide when you can do experiments, actually 4 facilities, and then one which is not for public use. 2 of the facilities where we do experiments quite often are the one in the UK, so this ICIS Brown facility, and the PSI, Polshire Institute in Switzerland. So these are the aerial photos of these 2 facilities, and both facilities give you opportunity to work on muon spectroscopy, and also they are a source of neutrons. Okay, so there is a plan of 3 new facilities in the next 5 to 10 years. One in US, one in South Korea, and one in China. This in China, I think, is the closest to realization at the moment. Okay, so it's quite, well, there's not a lot of facilities where you can do experiments. So, of course, there is quite a strong competition for the projects to get through. But eventually, of course, if you have a good project for a good case for muon spectroscopy, of course, you can perform these experiments in Europe quite easily. Okay, so now, again, the basics of the techniques. So this is now our muon, which comes into the sample. Let's say there is a static field. The muon will process, depending on the time before it decays, it will process by some phase. And what you measure then is the positron which is emitted. So this is the static. Okay? And in a static field, what you would measure is the polarization of the muon as a function of time. It would give you these oscillations. Okay? Now, if you reduce the field, yeah, reduction of the field means that the precession is lower. In other words, yeah, your signal, the polarization versus time, will now have precession which has lower frequency. Now, if you reduce the field, yeah, you don't get the oscillations anymore. Yeah? You end up with a simple monotonic curve. Yeah? In principle, it's not decaying, but due to the fact that there are also some effects of the fluctuating field, this gives you decay. Okay, so kind of a measurement that you can perform. One of the measurements is simply to measure the precession frequency, and this gives you an insight to static local field. For instance, if you have a phase transition from from a parameter to an order state, you would measure your local field, which would give you something like that. Okay? So this is the basic principle. What are the advantages of the technique? So I have to have some water. Yeah. So what are the advantages? The first advantage of this technique is that it's really extremely sensitive to magnetic fields. So it can measure magnetic fields of the order of a tenth or a few tenths of Gauss. Yeah, so it's really precise. And this is due to the fact that the magnetic moment of the muon is bigger than any nucleus, of course. It can cover broad fluctuation rates, so it can measure in this kind of range of fluctuations. Then another very important point is that muons can be implanted in principle in any material, and they are non-destructive. So they have this low energy, they do not make any damage to the system. Plus, they are implanted one by one. Okay, so if you have some bulk state and you perturb it locally, it's highly unlikely that you will perturb the macroscopic magnetic state of the cell. Yeah? So you really measure individual muons. You implant a muon and measure how it decays. And then another one, measure how it decays. So that's the basic principle. And then another very important point is also that you don't require a static magnetic field, as in ESR or NMR. Yeah? And this is due to the fact that muons are 100% polarized because of this parity correlation. Okay? So another strong point. Okay, yes?
It's worth adding the observation that even though the energy is low compared to chemical energy scales, the energy scale is large compared to the kind of energy scales that you find in, say, spin liquids.
Yes, sure.
So that it's true that it implants non-destructively in the sense when it's gone, you're back to where you started from. But while it's there, it can change the local.
It can change the local. It can also change because it's a charged particle. Yeah, it also changes structure locally.
So unlike photons or neutrons, which have no Coulomb energy.
Exactly. Yes. Yeah. So in this sense, yes. So there are some problems. Of course, I'm talking about advantages of each technique, but there are also some problems with each of the techniques.
I'm sorry, but I don't understand the basic principle. So each muon can decay only once, so I would have only
sure.
one.
Yeah, but then you run the experiment for some time, right? And then you just count the positrons which come to each of the. Usually you have two detectors. Yeah? So let's say your muon comes in like this, and then you have two detectors, this detector and this detector. And then you make the statistics of how many muons hit front detector and how many the back detector for some decay. I mean, for some time after the muon was implanted. So for each time, you get some statistics. And this gives you the curve which I was showing before. Yeah? Understandable?
But that's the same as any scattering technique.
Yeah, sure.
If you scatter X-rays
It's like
neutrons, you don't get bragg peaks.
Exactly.
Individual neutrons.
You
count how many.
You count at the end. Yeah, here it's time resolved technique. Yeah. So you measure at a specific time because you know you have a muon counter. Yeah, when the muon enters your sample, you know that, and then you know when the positron comes into your detector. Right. So you know what was the lifetime of the muon. So for any point on this scale, on the time scale, you can make a statistics of how many muons come into one detector or the other detector. Typically, it takes like several million actually events that you count. Yeah, but because the lifetime is pretty short, it's 2 microseconds, means that your measurements typically takes like half an hour or something like that. So it's not a really long. Yeah. But you measure individually, yes. You measure individually where each muon or where the positron goes from each of the muons that are implanted.
I would actually like to hear a more detailed comment about the previous question about the destructiveness of this measurement with respect to your magnetic media. So the energies are indeed quite low, and you perturb it significantly when you say the giant magnetic moment.
Yes, well. It's a question whether you transfer your energy to the magnetic system or not, right? So your muon stops, and this stopping of the muon goes through some ordinary process. It doesn't have to do anything with your magnetism, in principle. Yeah? You also don't change really the magnetic polarization of the muon. Yeah? And once you have a muon in your system, of course, it is addressed, of course. Yes. What is more important or more problematic is that it has a charge, electric charge. Yes. And it affects, of course, your crystal field locally. And this can also have an influence of the exchange interactions, for instance, so you have some local perturbation.
Yeah, this is also important, but this I more or less understand, at least qualitatively, although I don't know how to mitigate this effect in the experiment, but with respect to magnetic moment, it also has some energy of interaction between the moments that you're trying to measure and this moment and this magnetic moment, and in the sense,
sure. There is interaction, of course. This is why the vector, the polarization of the muon precesses, right?
Yes, but it has back action on the system that you're studying, right?
Yeah, but this is the same as in NMR actually, right? You have hyperfine interaction.
Yeah, but there we know for sure that this hyperfine energy scale is probably smaller.
No, but it's the same here actually. Here is also the hyperfine interaction. Usually it's actually dipole interaction in this case, and it is of very similar size than in NMR. The hyperfine interaction.
Okay, so the energy scale of this part of the interaction is also very small.
Yeah.
Okay, well then.
It's comparable to NMR. The moments are a little bit bigger, but usually muons don't tend to stop very close to magnetic moment because of the charges.
Yeah.
Okay. So usually they are somewhere in some vacant site in your crystal. Well, it depends on the system again, but if you have an insulator, usually it's the dipole interaction which is the dominant interaction, and this typically produces, on the muon side, it typically produces local fields which are of the order of, let's say, 10th of a Tesla or something like that. And this is very similar to NMR. It's not all, I mean, orders of magnitude in different energies. Okay. Okay, so let's go now to our experimental cases. So let's go back to this zinc brockentite where I told you that there are some indications of the spin on metal state or something that behaves very similar to spin on metal. So what we measured here, first of all, what I'm showing here is the time dependence of the muon polarization, and you can see that there are no oscillations present. So if there were some static fields due to the magnetic ordering, yeah, you would see oscillations. Actually, you do see oscillation in an analog material. So this is copper-free. This is well, this is how this is our system actually, copper-free zinc system. But there is also copper-4 system where you have on the zinc side you also have copper moments, and in this case it is well known that it orders magnetically, and this is the response of the muon polarization, so it has oscillations. In case of the copper-free, of this zinc brockentite, there are no oscillations. So down to the lowest temperatures, which are now, what, more than 3 orders of magnitude below the exchange interactions, there is no ordering happening. Okay, so the state is definitely dynamic. Then another set of experiments that we ran was a measurement of the night shift in applied magnetic field. Again, the same as in NMR. So now I'm plotting night shift yes, as a function of bulk susceptibility. Yeah, and what you can see here, which is different to the case of the NMR. If you remember before, in the case of the NMR night shift is saturated. Here you don't have any saturation. Here there is a really nice scaling between bulk susceptibility and muon night shift. This tells you that muons are actually not sensing intrinsic spins dominantly at low temperatures, but the defect spins, because the defect spins are the spins which have this vastly dominant contribution to susceptibility, right? And since our local susceptibility obviously scales with bulk susceptibility, it has to be that we are sensing the defect spins at low temperature. Okay, so now how the signal behaves with temperature. So this is a comparison of the temperature dependence of the muon night shift for 2 different fields, and you again have this saturation at low temperatures. This saturation the simplest explanation would be that since these defect spins are quasi-free, almost free, they would saturate, of course. Right? If you go to low enough temperature, high enough field, yeah, they would have to saturate. It turns out that this is not an explanation of what's happening here for a couple of reasons. One reason is that the value of this plateau here, of the night shift, from knowing the hyperfine coupling, which you can estimate from scaling of the night shift with bulk susceptibility, you can estimate the coupling constant, and from the known coupling constant, you can estimate what is the size of this, of the moment which corresponds to this plateau here. Yeah? And this size is quite small compared to the whole magnetic moment, right? So it's not fully saturated. You would expect something like whole low magnitude, because it's copper still not happening. Another point to note here is that there is no scaling with field, no scaling with the inverse of the field, which is again something that you would expect for free space. So this is not what's happening. So obviously there is some other interaction of defects, and defects, we also investigated the possibility of defects investigating between themselves. It's also not a case here, but the only possibility is that these defects are interacting with quasi-particle of the quantum spin liquid. Yeah? So you have this defect quantum spin liquid interaction, which is of this form. So you have your spinels, which are quasi-free, right, or free, actually in this particular case, they were completely free. And then, because your defect has a spin, this defect locally interacts with the spin of the spinels. Okay? And this is something that is well known, again, from metals. Yeah, in metal, there is this famous Kondo effect, which was experimentally known from the beginning of the 19th century. And what happens there in the metal is that you have, if you have defects which have magnetic moments in the metal, these defects interact with electrons there, through their magnetic moment. Yeah? And then you can have two cases. High temperature, there is a case of weak coupling, where there is only weak interaction, and these electrons only weakly screen the magnetic moment of the impurity. While if you go to low enough temperatures, there is this collective effect coming into play, which is that you have now strong coupling you need between your particles, electrons in the case of a metal, or in our case, these are spinels, of course. Yeah? So it's a magnetic analog of the Kondo effect. Okay, so this Hamiltonian actually explains this effect and gives you this, these are again numerical renormalization group calculations, which can give you this curve, the prediction of the Kondo effect in this case. And there are actually just two scaling parameters. One scaling parameter is the so-called Kondo temperature, which depends on the coupling strength between the spinels and the impurities. And the other free parameter is actually the amount of impurities. Yeah? And just by fitting this kind of experimental data, we get this amount to be within the range that was determined from other experiments, from heat capacity, susceptibility, and other interactions. Okay, so what's happening here is that, as I said, you have an interaction between spinels and local magnetic moments, and at low temperature, when you go below the Kondo temperature, there is a strong coupling regime, and you enter into a state which is basically how to call it. So it's well, I will show you in the next experiment actually. So what happens is that you enter into this regime of new quasi-particles that form the Fermi surface. So your density of states is enhanced in the Fermi surface. So this is now in the picture of strong Kondo coupling. Okay, so this was a static fingerprint of the Kondo effect through the muon night shift. And then there is also a dynamic fingerprint, which is the muon relaxation rate. Now the muon relaxation rate is proportional, in this picture of a spinel metal, is proportional to the square of the density of states of this Kondo resonance at the Fermi surface. Okay? And what is well known from theory, again, is that the Kondo resonance would split in magnetic field. So what I'm showing here is the field dependence of the Kondo resonance. Yeah? So if you are at low fields, you have a single peak, but then when your field exceeds more or less the value of the Kondo temperature, you end up in the regime where there are the two peaks are split. So you have split your contribution of spin up and spin down to the Kondo resonance. Okay, and with temperature, this Kondo resonance broadens, which means that at higher temperature, of course, you would require higher fields to split. Okay, so how did we measure it? We measure it again, as I said, through the field dependence of the muon spin rate, which is proportional to this value here. And as you can see, there is a critical field where the regime of the field dependence of this relaxation rate changes a lot. So here you're in the regime of a single peak in the Kondo resonance, and here you're in the regime of two peaks. So you have a sudden decrease of the relaxation rate due to the opening of this relaxation, the opening of this gap, splitting of the resonance. And it is predicted theoretically that it should be linear with temperature, and this is exactly what we see. And there is a finite critical field at zero temperature, which is given by the Kondo temperature itself. And indeed, if you estimate the energy scale from this field, you would see that it scales naturally with the Kondo temperature that was determined from the night shift experiment. Okay, so what's happening here is you have impurities. These are blue points, and then you have the spinels. This, of course, just schematic. It doesn't have any. There's no physical interpretation in terms of the picture itself, just the effect. So just schematic representation what's happening. So again, you have this impurities, and then you have spinels. And then at high temperatures, the spinels are more or less randomly yeah, randomly occupied lattice. But when you reduce your temperature, so this is the lower experimental temperature, okay, so run once more. At low temperatures, they tend to gather around impurities. So you enter this strong coupling regime. And they screen the magnetic moment of the resonance. Oh, good. Yes? So how much time? Oh, more, we are almost there, right? Okay, so maybe I will, there was a part also about neutron scattering, but okay, I covered the local probes, so maybe I will skip this. Yeah, we already had some discussion about this anyway, what you can measure. Maybe just the last slide actually. Okay, so these are some of our measurements, I will skip these, but maybe what is also our measurements. What is important is that this technique is Q resolved. Yes? So you don't integrate over Q like with local probe techniques. So in principle, you can measure your dynamic speed structure factor if you have crystals. Yeah, you can measure it over the whole Brillouin zone. And in the case of Herbert-Smith type, for instance, so these are results from 2012 that were published in this paper here in Nature. They were able to show that there is a spinum continuum. Yeah? So if you look at this loss, maybe, so this is where it's more enhanced. So if you go to the K point, which is basically, so this is this point, is the edge of the Brillouin zone, right? These points here, you would get magnetic excitations across broad range of energy. Yeah? So this is something that's very different from excitations which occur in magnetically ordered states, right? Where you have this spin waves which have well-defined dispersion. Here you don't have a well-defined dispersion, but rather you have really a spread of possible energies. And one of our contributions, okay, also to this system was also to show that this is not due to it's not due to dimer interactions between neighbors actually, but it's actually due to some chiral fluctuations that happen in this system. That's again theoretical prediction by finding temperature lunches. Okay, so with that, let me just summarize. So in summary, I would say that what I would like to stress here is the complementarity of techniques. Okay, so I showed you many different techniques, and each of these techniques have their own advantages and also some weaknesses, of course. Yeah. So what is very important from the experimental point of view is that if you're able to make measurements with complementary techniques, then you often get to a point when you can make some predictions that you would not be able to make just on the basis of one technique, for instance. Okay? And this complementarity comes from it's due to different perspectives. One perspective is that the techniques that I was mentioning, okay, I didn't mention elastic field scattering, but anyway, it's here on this plot here. So they have different time windows. So they can trace spin dynamics on different scales. Okay, so maybe some magnetic state would seem like an ordered state, yeah. But actually, if you do a complementary experiment, let's say a Newton experiment, yeah, which is really a snapshot measurement, yeah, you could see magnetic order, you could see magnetic backpeaks, but then you go to MUSR and you don't see order or NMR. Why? Because the fluctuations that are associated with this order are really on a short time scale. Yeah, sorry, long time scale. Small frequency. Okay, so this is one aspect of the complementarity. Then there is the second aspect that the sensitivity to local fields is really different. Yeah, so yeah, sometimes if you really want to see magnetic order, so it's usually very good if you go to MUSR experiments because they are really sensitive to that. You can really measure tiny magnetic moments. While with neutrons, you usually need to see magnetic backpeaks, you usually need quite big magnetic moments to observe them. Then there is this complementarity with regards to the Q space, right? So the local probes give you a Q integrated response, while scattering techniques can give you Q resolved response. Okay? And there's also this complementarity about the accessibility of different techniques, right? So there are techniques like NMR of ESR, which are lab-based, meaning that if you have a few hundred thousand euros, you can build your own laboratory. But on the other hand, there are techniques which really require large-scale facilities like neutron scattering or ESR, because it's impossible, of course, to make a spectrometers, lab-based spectrometer. It involves a lot of people, a lot of different knowledge, and a lot of money to run.
So is the x-axis followed?
Sorry?
Is the x-axis
Here? Yes, yeah, maybe, yeah. Yeah, it's logarithmic, of course. Okay, so with that, okay, one final slide is about the postdoc opportunity at the Josef Stefan Institute, if any of you would be interested. So we just got approval of our Marie Sklodowska-Curie co-fund project, and this, well, it's called the Slovenian Quantum Science Hub project. And this project will cover basically 40 postdoc positions at our institute in the next 5 years. And it will cover basically all the quantum science that goes on at the Josef Stefan Institute and also here at the Faculty of Mathematics and Physics. It will cover different fields, from quantum theory to quantum materials, so I focus on that one here today, to quantum technology and also quantum computing and information. So if any of you would be interested, of course, you should pay attention to, there will be calls associated with these positions, and the first call is expected to go out in about a year. Yeah? So in autumn we will start, or actually we will start the project in the next year. Actually, we have to still sign the agreement with the European Commission, and it's expected that we will be able to give out this first call in about a year. Okay. So with that, I would like to thank you for your attention. And if there are some questions, go ahead.
There's no questions.